All right, so let's pick up where we left off in the previous video, talking about compositions of functions. It's always easier for me to visualize what we're doing here. Instead of just diving into the composition of what happens when you substitute 2, it's always easier for me to do the composition, f of g of x first and then substitute 2. Now you can do it if you want to just substitute 2 into the composition, but kind of works the same way. You would substitute 2 into this function right here, and then whatever you would get, you would substitute that into x for the f of x function. But we're going to do it my way since I have control here, and we'll see what happens. So again, you start with the g of x function, and you substitute that into the f of x function anywhere where you see an x. So this becomes 3x to the third plus 6. And once you have that composition, you can then just substitute the value of 2 in. So 2 to the third power plus 6. And just make sure that you're not making the mistake with the exponents. A lot of students say that 2 to the third power is 6 because they do 2 times 3, but that's obviously not the case. It's 2 to the third power, which is 2 times 2 times 2, which is 8. So this is going to be 8 times 3, which is 24, plus 6, which is 30. And as I said before, what you could do is you could just do the 2 to the third power, which is 8, and then take this 8 and substitute it in for x. You would obviously still get the same answer because we would get 2 to the third power, which is 8. 8 times 3 is 24. 24 plus 6. So it works out the exact same way, whether you see the full composition of the function before you substitute, or you just substitute the value. Over here, this is a little bit different. This is g of f of x. So this time, you're going to take the f function and substitute it in for g. So this one is going to be, again, g of f of x is equal to, and this time we're going to take this function, all this polynomial part, and we are going to substitute it in for x in the g function. So that's going to give us 3x plus 6 raised to the third power. And right now, we don't know how to deal with this. We're just going to leave it alone. Later on in the course, we're going to learn how to multiply polynomials. Matter of fact, a little bit later on in this chapter, we'll do that. We'll be multiplying polynomials, but we will go ahead and do that then. Some students think that you can apply exponent rule that has this term here, or these terms raised to the power of 3. They think that they can just kind of like raise 3 to the power of 3, x to the power of 3, and 6 to the power of 3. That exponent rule only applies when you have a monomial inside the parentheses. The second you put a polynomial, a binomial, a trinomial, or above inside the parentheses, and you have an exponent out here, you can no longer apply that exponent rule. So you've got to do something else, which I said we'll learn later on in this chapter. All right, so the simplest polynomial function is the identity function, which is just y equals x. So basically all the values are exactly the same. Of course, there you have the graph here. 0 equals 0, 1 equals 1, 2 equals 2, 3 equals 3, and then same thing for the negatives. And all linear functions are have a domain of negative infinity to positive infinity and a range of negative infinity to positive infinity, except for those special cases. So when you have the special case of, let's say, the horizontal line, obviously this one is going to have a domain that's from negative infinity to positive infinity, but the range is very simple. The range is always 2. There aren't any other values other than 2. So the range of this guy would just be the set that has 2 in it. That's the only value that's in the range, but the domain would still be the same. It'd still be from negative infinity to positive infinity because it's for all the way to the left, all the way to the right. Nothing is skipped out. So the domain of the function is still all real numbers. Okay. Over here, you could take a look at this and say, all right, well, we have a parabola here, and we can figure out what the shape is. We'll graph this more in depth later on in the course when we get to chapter 8, where you're going to substitute values in, and you substitute 0. 0 squared is 0. 1 squared is, 1 squared is 1. 2 squared is 4. Negative 1 squared is 1. Negative 2 squared is 4. So that's where this table is built from. And you can see that this is going to continue going on forever this way, continue going on forever that way. So the domain is all real numbers, and the range is a little bit different again. There's a clear defined minimum value here. You can see that the lowest that this gets is 0, and then it gets shot back up again. So you have a minimum value of 0, and it looks like it does get to 0 because you can see it right here, and it's going to head all the way to positive infinity. Okay. And then you have your cubic function. It works almost the same way, except instead of not allowing things to be negative, which is why this got shot back up for the square, the cubic allows the values to be negative if they are, because when you raise something to the third power, if it's negative, it's going to stay negative. So you have negative 1 to the third power is negative 1. You have negative 2 to the third power is going to be negative 8. So this is going to head all the way down to negative 8. So this probably isn't the best picture because this actually looks at like it's going to be here at 5, but it's going to continue down. When x is negative 2, it's going to be a y value of negative 8, which is down here. So it's not the best picture of what's going on here, but you can see that it is a little bit different. Okay. So let's take a look at this one, and we'll give the domain and range. So essentially what we're going to be asked to do is we're going to substitute these values into our function to figure out what corresponding y values we're going to get. So 0 squared is 0, and 0 times negative 2 is still just 0. So we have 1 point, and there it is. So we're going to go ahead and graph that. Okay. And then we'll start with, I don't know, it doesn't matter which ones, we'll just do this. So 1 squared is 1. And again, I'm just substituting these values in kind of like in my head, right? If I wanted to do it out, I could do it. So positive 1, we're doing positive 1 first. So positive 1 squared is 1, and then 1 times negative 2 is negative 2. And then we'll do the next one, 2. So 2 squared is 4. 4 times negative 2 is negative 8. So we'll go ahead and graph those points. So there's 1 here, 1 here. My 0, 0 disappeared. 2, negative 8 is down here. This. And we'll do the same thing with the negatives. So negative 2, substitute negative 1 in. Negative 1 squared is still just 1. 1 times negative 2 is negative 2. So we got the exact same value again that we got before. And last but not least, should be no surprise to anybody, we are about to get the same thing again. So even though we're substituting negative 2 in, we're still going to get negative 8. So negative 2 squared is positive 4. Positive 4 times negative 2 is still negative 8. So we will learn later in chapter 8 that there's symmetry with these parabolas. So you can see that this parabola is kind of doing this. Actually, wasn't bad. Pretty impressed with myself here. Oh, that was spoke too soon. Of course, that's what's Murphy's law, right? So the domain, most functions have a domain that's all real numbers, and this one is exactly the same as well. So it's from negative infinity to positive infinity. The range here is a little bit different, obviously, because you have a maximum value of 0, and then all of the points are below 0. So it's going to negative infinity, and it has a maximum value of 0, which has a square bracket. And this is a parenthesis, because obviously when you're dealing with the infinity symbols, you're always using a parenthesis. All right, so 4.4, as I promised, we were going to learn about multiplying polynomials. So here we go. And most students do pretty well with multiplying polynomials. They sometimes are so good at it that they end up doing it when I ask you to add and subtract them for whatever reason. So we just make sure that you're doing the correct thing when you're being asked to multiply. You actually multiply. When you're asked to add, you add, subtract. But obviously you can change it to addition if you wanted to by using the technique that I showed you earlier in an earlier video. So let's find this product. So we're multiplying monomials. So a monomial is still a polynomial, so we're still going to be able to do that. So this is going to be 8 times 9 is 72. K to the third times k to the first is going to be k to the fourth. And then y to the first times y to the third is y to the fourth. So that one's done. This is just a straight up application of our exponent rules that we learned in the previous video. So this one, we are going to distribute this negative 2r into both the 9r and the minus 5. So if this were just a negative 2, this is something that we did back in chapter 1 using the distributive property, but it's a little bit different now because we have an r out here. So we're also going to be applying the exponent rules as well. So you have negative 2 times 9 is going to be negative 18. And r times r is r squared. So that deals with the first loop here. So negative 2r times 9r is negative 18r squared. Now we have negative 2r times negative 5, which is going to be positive 10r. So negative 2 times negative 5 is positive 10. And then the r is just coming along for the ride here. Okay? So easy peasy. So finding the product here between two binomials, what I usually do is either the FOIL method or I use something that's called the box method. So I'll do the box method here first because most students are familiar. They have some familiarity with the FOIL method already, but some students have never been introduced to the box method. So I will enlighten you with that right now. So let's take a look. So the box method sounds exactly like what it sounds. You just make a box and it's going to be a 2 by 2. And the reason why it's a 2 by 2 is because it's a binomial times a binomial. If it was a trinomial times a trinomial, it would be a 3 by 3. So we put this 2k minus 5m along the top, and then you do the 3k plus 2m along the side. And it doesn't matter if the 3k plus 2m is on the top and the 2k minus 5m is on the side. That doesn't matter. That doesn't change anything. Multiplication is commutative, right? So it doesn't matter, where you end up putting these. It's just they need to be together, though. So you can't put like the 3k here and then the negative 5m down there. That's going to change that binomial. So this is one binomial and this is the other binomial, but it doesn't matter whether it's on the side or the top, so long as they're together. So we have 6k squared right there. This is going to be negative 15km. This will be, again, 2m times 2k. It's just behaving exactly like a multiplication table would do, or a Punnett square for those of you who are sciencey. And then we have our 2m times negative 5m, which is going to be negative 10m squared. And the next thing that we're going to do here is we will combine our like terms. So these, once they're in this box here, the terms are not going to change. The coefficients will if we can combine them, but we're not going to be multiplying anymore. We already did the multiplication. So now we're playing matchmaker of do we have like terms? And we obviously do. We have the km here and a km there. So our final answer is going to be 6k squared minus 11km and then minus 10m squared. And some students are asking, well, I got 11 or negative 11 mk instead of km. All right, whatever. Again, multiplication is commutative, so it doesn't matter if you have km or mk. It's still the same answer, and MATLAB knows that too. Okay, so we'll find the product here as well. I'll just continue with my theme of my box method since it is the, I think, most obvious way for me to do it. The reason why I like this is when you start getting into more complicated polynomials, let's say you have a 4-term polynomial times a 4-term polynomial. That's 16 individual sets of multiplication that you need to complete. So if you're not organized, there's a really good chance you're probably going to miss something where this box method doesn't allow it, because that means that you have an empty square and you shouldn't have one. So as long as your box is filled up, you know that you did all the multiplication that you should have. Maybe you still made a mistake with combining by terms, or you actually made a mistake with multiplying them, but at least you know that you did everything that you should have done. Whether you did it correct or not that remains to be seen. So we've got 4x minus 3y, and you've got 3x minus y, and we're just going to complete our multiplication table again. So this will be negative 4xy, and then positive 3y squared. Cool. And once again, we have like terms, so we'll knock those out. You have 12x squared minus 13xy plus 3y squared. And that's all she wrote. So once again, this is definitely where the box method is super handy, I believe, because you have a 4-term polynomial times a binomial, and that is 8 sets of multiplication that you need to complete. So I'm going to not do the vertical method, which just behaves like a regular multiplication table for those of you who've never seen it before. Maybe I'll start it over here, and then I'll show you the box method up top. So again, it just takes an extra step here to actually draw the box out. It's not a super long step, but it does get a little tedious. So it's a 4 by 2, and you've got 2a there, and negative 5. So I'm just going to show you the first line of the vertical method, which is what they're saying for us to do here. So basically, you're just going to take this negative 5, and you're going to multiply it into everything in this top row. So that's going to give you positive 15. This is going to be negative 10a. That will be positive 30a squared, and that will be negative 25a to the 3rd power. And then the next thing, just like with a regular multiplication, when you move to the next one here, you kind of like skip a spot, right? So you just, instead of like putting things right here, you just put it in this column right there. So the same thing happens. You do 2a times negative 3, which is negative 6a, and now you can see that your like terms are lined up, okay? So I'll just do the box method. I'll complete it out, and you'll see that all the terms are still going to be there. So you should be happy enough. So 10a to the 4th, this is negative 12a to the 3rd. You have 4a squared and negative 6a. So there's our negative 6a right there. And now you have negative 5 times 5a to the 3rd, which is negative 25a to the 3rd. So we're going to get this whole row right here again. So this is going to be 30a squared. That is negative 10a, and this is positive 15. And now we just combine our like terms. We don't have to look too far for them. They're right here in the diagonals. So we just combine them. So 10a to the 4th, you have negative 37a to the 3rd. You have 34a squared, negative 16a plus 15. And that, believe it or not, ladies and gents, that is your final answer, because again, you're in descending order, 4, 3, 2, 1, 0. So you're in descending order, you're a single variable. You have no like terms because you have all the same variables except they're all different exponents, which means they are not like terms. You cannot combine them. Okay, so hopefully, you find a method that works best for you, whether you like this vertical method. Very few students end up using this one. They usually use FOIL, or they use this box method to be able to complete their multiplication. All right, so here is the FOIL method formally introduced. So it's your first terms, your outer terms, the inner terms, and then the last. It's just an acronym for first, outer, inner, last. So they use the FOIL method, one of our famous F words in math, right? Lots of famous F words. So this one just says to use the FOIL method, so I will appease the book by using the FOIL method. So this says firsts, which is going to be 10r squared. So then it's O, so outer. So that's going to be our outer terms, which is negative 25r. Then it says to do the inner terms, which is negative 6r. And then it says to do the last terms in each set of parentheses, which is going to be positive 15. And then you just combine like terms. So you should have 10r squared minus 31r plus 15, and that's all for this problem. Okay, and you would get the same answer using the box method or using the FOIL method. Obviously, it's just two different methods to get the same answer. Okay, so we'll do this one using the FOIL method as well, since it's telling us to do so. So we've got 8y squared. So first, outer, this is going to be plus 12yz, inner, minus 2yz, and then last, minus 3z squared. And we're just about there. We just combine our like terms, which are these two terms right here, and that will give us 10yz minus 3z squared. All right, so this is going to be pretty critical later on in the course, especially in chapter 5 when we start factoring, and also in chapter 6 as well, when we start using our new factoring skill to do other things in math. It's not super critical right now. Oops, what just happened? Aggressive here. It's not super critical right now, but definitely later on in algebra, when we go from this, so we're going to start with this, and we need to turn it into that. That's when it's going to be very critical for you to be able to recognize that you have this difference of 2 squares. That's what this is. So it's a difference of 2 squares. Essentially, you have the same stuff in both sets of parentheses, so an x and an x, a y and a y, so the same stuff in both sets of parentheses, but you'll notice that the operations are different. So it's not, again, super critical to recognize it right now because you're probably just going to do either the FOIL method or the box method to get this result. But if you can recognize it, you'll definitely get your answer a lot faster. So I'll do this one here just to kind of bang this out quickly so we can see what's going on. So again, if you do the shortcuts, okay, if we take a look at this shortcut, it says if you recognize that you have this difference of 2 squares, which means you have an m and an m, same stuff, a 5 and a 5, but your signs are different. So your operation is different, one's plus, one's minus. The shortcut says square the first term, square the second term, and subtract them. So the shortcut says square the first term, m squared, square the second term, 25, and subtract them. So that will be the result if you recognize that you have a difference of 2 squares. Now you could always check your answer by doing the box method or the FOIL method, whatever floats your boat. So we've got m plus 5, m minus 5. You've got m squared here. M times m is m squared. This is 5m. This is negative 5m. And this is negative 25. You can see here that these cancel each other out because one is 5m minus 5m. They're going to go away. So your middle term, just your degree 1 term, is canceled out, and you're left with your m squared and your degree 0 term. So let's do our shortcut here for this one just so we can get through. And it's, again, you recognize that you have this difference of squares situation, same stuff in both sets of parentheses. One's minus, one's plus, it doesn't matter what that order is. Multiplication is commutative. So the shortcut says square the first term, x squared, square the second term, 16y squared, and subtract them. Done. So there's your shortcut. And if you are probably doing this using the box method, you're still drawing your box. Over here, we'll do this one. So I'm going to do that first. So I'm going to, again, use the shortcut, square the first term, square the second term, 49, and then I'm going to subtract them. And now I'm going to put these just in brackets real quick because all I did was recognize that this was my difference of 2 squares. So I applied the shortcut to get that. But now I have this 4y squared on the outside that I need to distribute in. So that's going to give me 4y to the 4th, and that will be 190. Let's see, 196 and y squared. Right. Cool. So this one again is where it's really critical to recognize that you cannot apply the exponent rule to this situation. You cannot just square these two terms and then call it a day. You really need to either recognize this shortcut if you want to, or you have to do the FOIL out or the box method out. You've got to actually do the multiplication of these binomials, because remember, this x plus y squared is really x plus y times x plus y. That's really what it is. So these are two binomials that you're supposed to be multiplying together, and when you do that, you end up getting this situation, okay? So again, you could do the FOIL method if you wanted to prove that, or you can just take the book's word for it that that's what happens when you square x plus y, and this is what happens when you square x minus y. Notice the only thing that's different is there's a plus here, minus here, minus there. Everything else is exactly the same. All right, so let's bang this out using this shortcut, okay? So the shortcut says square the first term, t squared, square the second term, that's going to be at the end, that's going to be plus 81. And since this is a plus, you know that there's going to be a plus here. To get your middle term, you multiply these together and then multiply by 2. That's what this says. So multiply the terms together and then multiply by 2. So multiply the terms together and multiply by 2. So you're going to get t times 9 is 9t, times 2 is 18t. And we're done. Over here, we'll do it again using the shortcut. So square the first term, 4m squared. Square the second term, you've got 25, and it's a plus here, so this is going to be a plus as well. Multiply these together, you get 10m, and then multiply by 2, you get 20m. And there you go. There's your shortcut in a nutshell. One more time. So we'll square the first term. Square the first term. 9 is what happens when you try to go too fast. 9k squared. Square the second term. 4n squared. There's a minus here, so there'll be a minus there. When you multiply these together, you get 6nk, and then multiplied by 2, you'll get 12nk, and this is a plus there. And that is how you get these binomials, squaring binomials, using the shortcut. Of course, you could FOIL it out or box method it out to confirm these, but I'm pretty confident that these are good to go. All right, this is where things get interesting. So now you have this x plus 2 raised to the 4th power. So what I would do with this is I would sort of break this up a little bit so that it was x plus 2 squared times x plus 2 squared. I know it seems weird because what this is an application of your exponent rules. It says that when you're multiplying like bases, this base right here is the same as that base right there, you are adding the exponents to get 4. So what I did is I just broke it up. I just broke it up into 2 separate ones, which I can use the shortcut for, right? So I know what this guy is going to be. It's going to be x squared plus 4x plus 4 using the shortcut, right? Again, when I had this binomial squared, I can use the shortcut to get that answer, which means this is also going to be the exact same thing. It's going to be this x squared plus 4x plus 4 as well. And now you have a trinomial times a trinomial. So what I will do here is I will do a box method with a 3x3 so I can stay organized, because I don't want to miss anything, especially with 9 sets of multiplication. That's what's going to happen here. So 4x plus 4, x squared plus 4x plus 4. And now we're going to do all of these multiplications out. There are lots of them. There are 9 of them, sorry. I don't know where that 12 came from. Wild. 16x squared, 16x. This is 4x squared. This is 16x. And there is our last one of 16. What's really nice about this box method, if you haven't picked up, is since we were in descending order in the original problem, all of our like terms are kind of living right here in the diagonals. We don't have to search far and wide for them. That is not a coincidence. So our final answer here is going to be x to the fourth plus 8x to the third plus 24x squared plus 32x plus 16. And I got that just by combining all of my like terms. All right, so multiplying functions sounds really daunting, like it's going to be a big problem for us, but we learned earlier that when you're adding and subtracting functions, it behaved a lot like adding and subtracting polynomials, and there's no difference here, okay? So let's take a look. So we've got f times g. Remember, this is different than f of g. It's not the same. So this is f times g of x. So what we are going to do is we are going to multiply the polynomial parts together. So we are going to multiply these together and see what happens. So that's going to give us 3x plus 1 and 2x minus 5. I'll use the FOIL method. Variety is the spice of life, right? So this is going to be 6x squared plus 2x minus 5, and I know I'm not actually doing the FOIL method, but you get the picture anyway, minus 15x, and you'll get 6x squared minus 13x minus 5. So there's your, quasi-FOIL method that I did in a different order, but who cares? Multiplication is commutative. We're just combining like terms with these end results anyway, so it doesn't matter what way you do FOIL. All right, obviously, it wouldn't spell FOIL if you did this another way. And then last but not least, they say go ahead and substitute 2 in, so that way you can get your f times g of 2. So f times g of 2 is going to be 6 times, 2 squared minus 13, oh boy, times 2 minus 15. So this is going to be 4 times 6. Remember PEMDAS, exponent before you multiply. So this is going to be 24 minus 26 minus 15, which is going to give you negative 17. Done. Okay. Cool. Okay, I just realized that this is supposed to be a 5. I wrote a 15 there, which is why things got a little crazy over here. So that should just be a 5. That should be a 5, which means this is going to be a, let's see, negative 2. That should just be minus 7. So that hopefully should fix things pretty well here. Let me just double check. Yep, and we are good to go. So the double check is to, again, what you can do is you can substitute the 2 into each individual function and then multiply them together. So if you did 3 times 2 plus 1, you would get 7. If you did 2 times 2 minus 5, you would get negative 1. And 7 times negative 1 is equal to negative 7, which is exactly what we got right there. So again, don't go too fast. Don't have typos. Double check your work. So that way, if you are going too fast, you can at least check your answer, okay? And hopefully catch any little snafus that you made, like I just made, but was able to catch. All right. So dividing polynomials. This is probably one of the least favorite sections of students in my classes when I'm usually teaching these as a lecture. So we'll see how you guys are able to do it. So this says that you are taking a polynomial, there it is, a plus b, and some polynomials, binomial, and you're dividing it by some monomial, c. You are allowed to divide and conquer, split it up into individual fractions that you are dividing a and c, and then B and C. And if you can simplify A and C and B and C, then you need to do that. You need to write each quotient in lowest terms, aka simplify. So again, what this says is that you can split this up so that it is written as 10x squared over 5 minus 25x over 5 plus 35 over 5. And then once you do this, you have just like individual division problems that you need to complete. So this will be 2x squared. This will be minus 5x, and this is going to be plus 7. Done. So dividing a polynomial by a monomial is just generally straight up application of the exponent rules that we learned in the previous video. Okay, so let's take a look at this one. A shortcut, if you don't want to have to rewrite the whole thing, a student did this in one of my classes a while ago, and I've been using it ever since, is they just kind of did this and said, all right, I'll just rewrite this again, so that way they don't have to rewrite the whole thing. And I thought it was brilliant. I was like, I love this. I'm going to keep using that. So this is 4x to the 4th divided by 4x to the 3rd. The 4's cancel, and the exponent rules tell us that you're left with just an x to the 1st. Over here, the x to the 3rds cancel, and you're left with negative 7 over 4, which is already in its simplest form. Over here, 12 and 4 simplify to be 3 over 1. So this should be 3 in the top, 1 in the bottom. We don't need to write that yet, though, because we have an x down there. You have an x squared divided by x to the 3rd, and our exponent rules tell us that we should have an x in the denominator. You would end up with a negative exponent, which you can't have. You push it to the denominator, which makes more sense if you look at it as you have 3 x's in the denominator, you have 2 x's in the numerator, you have 1 extra x that didn't cancel left in the denominator. So we'll do this last one, a to the 3rd, b to the 4th, a to the 3rd, b to the 4th. So that way, again, just being kind of lazy here. So you've got 6 left up there. There's no numbers in the denominator to cancel, so all the numbers that are up here are going to stay there. The b to the 4ths are going to see you later, and you're left with an a in the denominator, very similar to why you have an x over here in the denominator. A to the 3rds cancel. Again, your 9 is still going to be up there, and over here your b is going to be in the denominator, and your 4 is not going to cancel. It's still going to be up there. A to the 3rd, b to the 4th, and you are done. So there's your final result with this problem. So multiplying a polynomial by a monomial is just straight up application of the exponent rules. This is where things get a little bit tricky, okay, is when you're taking a polynomial and you're dividing it by a polynomial. You need to use something that's called polynomial long division or synthetic division. I'm going to show you polynomial long division, okay? So what you do is you take this k plus 6, you put it on the outside, just like you would do long division, and you put your 2k squared plus 17k plus 30 on the inside. And then what you do is you see what happens when you take this k, again, just the k for a second. What would happen if you divided this first term by k? You would get 2k, because one of the k's would cancel, right? So that's what we're going to do, is we're going to take this 2k squared, and we're going to divide it by k, and that will give us 2k. Notice I put the k right above the 17k. I'm trying to line up my like terms as best as I can. So once you figure out, again, what would happen if you took this 2k squared and divided it by k, you would get 2k. You are now going to take this 2k and you're going to multiply this into both of these terms now, one at a time. So 2k times k is 2k squared. No surprise there. This is supposed to happen. These are supposed to be the same this first time. And then 2k times 6 is going to be 12k. And what we do is we put these in parentheses and we subtract them, just like you would with regular long division. Once you do the multiplication, your next step is to subtract to see what the remainder is, right? So the same thing is going to happen here. So I'm going to subtract 2k squared minus 2k squared. They will cancel out. 17k minus 12k is 5k. And then we know that based off of regular long division, the next step is to bring down the next term. So we're going to do that. So we've got 5k plus 30. And then we do it again. We're going to see what would happen if we took this k and divided it into 5k. So 5k divided by k would be 5. And once we get this 5, we are going to multiply it in to both the k and the 6. Okay, so that's going to give us 5 times k is 5k. 5 times 6 is 30. And we are now going to put these in parentheses and subtract. Cancel, cancel, remainder is 0. Which means this polynomial, this trinomial, is divisible by this binomial. As a matter of fact, the result here is this 2k plus 5. If you wanted to check your answer, if you get a 0 remainder like we have right here, if you check your answer, if you do 2k plus 5 times k plus 6, you should get back to this numerator over here. So let's just do the FOIL method real quick. I'll try not to screw it up this time by going too fast. So 2k squared, outer is going to give you 12k, inner is going to give you 5k, last is going to give you 30, and then when you combine like terms, you get 2k squared plus 17k plus 30, which is exactly what we have over there. Okay, so that is polynomial long division in a nutshell. So my guess is that, I'm going to do another example, but my guess is that most of you will probably have additional questions on this. Please ask them either on Wednesday or Friday of our Q&A sessions. Make sure that you're looking up, stay to the end of the video because we're getting towards the end here, so that way you know what you're doing with these polynomial long division. Okay? So we'll do this one now. So x plus 2, and then that's on the outside, and you have 4x to the third. This one's neat because you see how we have a missing x squared term? When you're doing polynomial long division, you want to make sure that you have all of the terms. And you have a missing term here, so we need to sort of artificially put that x squared term in here. And the way that we do that is we make the coefficient 0 x squared. So if this were a 0 out front, this really doesn't need to be here, right? And that's why it's not over here. But in order to do polynomial long division effectively, we really should put this term in there. So plus 3x minus 8. And again, see how many times x goes into 4x to the third. It goes in there 4x squared times, right? If you took this 4x to the third and you divided it by x, you would get 4x squared. Do the multiplication now. You get 4x to the third, you get 8x squared. Okay, again, I don't want all these loops everywhere, so I'm not actually showing you that multiplication, but this was 4x squared, which is 4x to the third. 4x squared times 2, which is 8x squared. Put it in parentheses, subtract, and you can hopefully see why I put my artificial x squared term here, so that way I had a place to put this, right? So these cancel, no surprise there. You have 0x squared minus 8x squared is going to be negative 8x squared. Bring down our next term. Again, take this x, see how many times it goes evenly into negative 8x squared, which is negative 8x times. Do the multiplication now. You get negative 8x, no squared, no surprise there. And this one is going to be negative 16x. Again, put it in parentheses and subtract. So these will cancel, no doubt about it. This becomes 19x x, because remember, 3x minus negative 16x means you're supposed to add those. You get 19x minus 8 by bringing down my next term. And we're pretty much done now. We're going to have 19 here because when you take 19x and you divide it by x, you're just left with 19. And sort of running out of space, so I'll have this 19 minus 8. Just rewrote this over here so I can give myself more room. And that's going to give me 19 x, and 19 times 2 is 38. So this is going to be 38, and I'm supposed to subtract these. So these will cancel for sure, and this is going to be positive, actually negative 46, right? Negative 46. Negative 46. You can tell it's getting late. So that's negative 46 is the result there. So this one has a remainder. It has a remainder of negative 46. So this is your quotient. So this is your quotient, what happens when you divide. This is your remainder. The way that you write this answer out is you write it this way. 4x squared minus 8x plus 19. Since this is minus, you do minus 46 over what it was that we divided by, which was x plus 2. So that is 2 videos with respect to polynomial long division. And that is it for this video, and that is actually it for chapter 4 as well. So thanks for tuning in, and I'm looking forward to meeting with you all on either Wednesday or Friday, or potentially both. So thanks for tuning in.